All right. Hi, guys. I apologize for not being there with you today, but I thought we'd walk through our I do, we do so that you can then go ahead and work together on the rest of the problems. So, as usual, I've done the first problem for you. Um, and we have to recognize that we're talking about an elementary reaction. So, when we talk about elementary reactions, unlike an overall reaction, we can assume that the rate law can be inferred from the stoichiometry of the problem. So, first question is, what is the overall reaction? So, in order to figure out an overall reaction, we're going to look at each of the reactions and we're going to see if there are any intermediates. So, we can see that in our first reaction, our two molecules of hydrogen iodide have come together to make one molecule of dihydrogen diiodide. And then in our second reaction, that molecule of dihydrogen diiodide decomposes to give us a molecule of hydrogen and a molecule of iodine. And so this intermediate here can be crossed out, and we're left with just the two hydrogen monoiodide forming hydrogen and iodine. So that's our overall rate law for the reaction. Now, when it comes to writing a rate law for an elementary step, we just use the coefficients as the orders or the exponents in the rate law. And so we would write our differential rate law, rate equals K times the concentration of hydrogen monoiodide squared, because there's a 2 coefficient in this equation. Okay, so our next problem says gaseous cyclobutane breaks down into 2 gaseous ethylene molecules via a single step unimolecular reaction. So unimolecular means one molecule. We talk about unimolecular, dimolecular, and termolecular, meaning 3 molecule types of reactions. So this is telling you that we're just starting with one molecule. It asks us to write the balanced equation for the reaction and then write the rate law for the reaction based on the stoichiometry of the elementary step. So I'm going to ask you guys to pause me here and go ahead and do this on your own, and then you'll unpause and we'll make sure that you're on the right track. So first thing I'm going to do is write down the gaseous cyclobutane, C4H8. Gas breaks down into 2 gaseous ethylene molecules, C2H4, and that's also a gas. So that's our balanced equation, and now we're going to write the rate law based on the stoichiometry of this elementary step. The coefficient of this is 1, so my rate law is going to be rate is equal to some constant K times the concentration of the cyclobutane raised to the first power. And we can write the 1 or we can leave it out. Okay, so pretty simple and straightforward. I think you guys can manage this. I am going to go ahead and talk about number 3 here on the you do part. It asks us about which is the more likely reaction mechanism. So what I want you to think about is just really common sense here. In reaction A, we have 2 iodine monochlorides reacting with 1 hydrogen to form 2 hydrogen chlorides and 1 iodine, and it assumes it happens in a single step. In reaction B, we have iodine monochloride reacting with hydrogen to form hydrogen iodide and hydrogen chloride. And then in reaction 2, second step of the mechanism, we have hydrogen monoiodide reacting with iodine monochloride, so this is the intermediate produced in the first step, to produce hydrogen chloride and iodine gas. So, when we think about collision theory, in order to have an effective collision, you have to have sufficient energy and correct orientation. That's much less likely to happen if we have to have 3 compounds bumping into each other at the same time. And so our bimolecular reaction here is always going to be much more likely than a termolecular reaction. Okay, I think that answers that part. All right, let's go ahead and move on to the second part of today's lesson. So it says, given the following reaction, which set of reaction conditions will result in the highest reaction rate, and explain in terms of collision theory. So the things you have to be careful of here, the temperatures are all the same, so we know the temperature is not going to affect it. The size of the container is changing, and the number of moles are also changing. So we want to think about concentration rather than just moles. And so if we look at experiment 1 and experiment 2, in both cases, the concentrations are 0.5 molar because the number of moles is doubling, but so is the size of the container. Whereas in reaction 3, we have the same number of moles as in reaction 1, but we have a container that's half the size, so the concentration is going to be much higher. So experiment 3 is going to result in our highest reaction rate because the particles are concentration are higher, and therefore they're more likely to collide with one another. Okay, so now for the we do. So these are our Maxwell-Boltzmann distributions. Now we're not looking at different sizes of particles or masses like we have before with Maxwell-Boltzmann. We're just looking at the number of particles with a particular speed and therefore a particular energy. So it's asking us on this first graph to add a line to represent a very low activation energy. That line is going to be a vertical line, okay, because speed is proportional to kinetic energy. Well, the square of speed is proportional to kinetic energy. And on the second graph, to add a line to represent high activation energy. And then it asks you to explain why you don't see a large increase in the reaction rate when the temperature is increased if activation energy is low. So again, I'm going to ask you guys to pause me, work through this together, and then come back and check. So if I have a low activation energy, like an activation energy of this is a low activation energy. And then if I have a high activation energy, that line is going to be much farther to the right. So this is my low activation energy, this is my high activation energy, and you can see that when you have a low activation energy, even those particles that are moving slowly, or at a low temperature, most of those particles still have more than the activation energy. But when we have this high activation energy, very few of our cold molecules have enough energy, not very many of our medium temperature molecules, and many, many more of our high temperature molecules have enough to exceed the activation energy. So if our activation energy is low, heating the molecules up and therefore speeding them up isn't really going to change a lot because we already have most of our collisions having enough energy to react. Okay, I look forward to seeing you guys tomorrow. Thanks.